Hi folks, this is segment 7 of FEA Basics. You may recall that when I started these segments, I mentioned in segment 1 that a three-dimensional object which is made of uh, structure with some support or restraint and some forces and load can be thought of as an interconnection, a complex interconnection of masses and springs, which I symbolically denoted it by a diagram like that. In general, it is difficult to explain how finite element works when I look at full generality like this. However, there's one special case that actually we can make sense of whatever I told you here. But in order to do that, I need some basic machinery first. So let us take a bar which is axially loaded. It has a length L, it has a cross section A, and it's made of material with a Young's modulus E. Young's modulus E. All right. If I ask you what is the stress in this bar, you're going to say S sigma equal to F over A, force over area. But remember that the stress at a point is actually made of 6 components, 3 components of normal stress and 3 components of shear stress. When I write something like that, implicitly I'm saying that all the stresses all the other 5 stresses are much smaller compared to this axial stress, and therefore they are being ignored. All right, so once we have the stress, then out of this, we can calculate the strain. And the strain is going to be simply stress over Young's modulus. Therefore, it's equal to F over AE. Now, what is this strain itself? The strain itself is the change in L divided by the original length. That's how strain in the normal strain in this in the direction of the load is defined, and therefore this is equal to F over AE. If you go from this and find the F over delta L, F over delta L, you're going to get, let's see, you're going to get AE over L. And what is this thing? This is force over displacement. And force over displacement is exactly what we mean by stiffness. This is stiffness. Which means that the stiffness of this bar, the stiffness of this bar, which we can denote it by K, stiffness of the bar, is equal to AE over L. So does this not mean that if you have a bar like that, and it's made of material E, cross-sectional cross-section A, and length L, doesn't that mean that we are saying that this is equivalent to a spring with a stiffness of AE over L? Well, that's exactly what this thing means. So, in the case that my three-dimensional object is really made of these axially loaded members, then we can represent it with a collection, essentially, of springs with the appropriate stiffnesses. I'm going to concentrate only on static problem. Concentrate only on a static problem. So suppose I have a situation like this. So I have 4 bars made out of let's say steel. This is steel attached to another bar that is made out of aluminum, attached to another bar made of copper, and then perhaps another bar made out of also copper. And let's hypothetically say that this, for example, uh, this end is subjected to a force F. A slowly varying force F, which means that I can solve this thing as a static problem. All right, so let's say that the length of this bar is L1. Well, actually, let's do the following. Let us replace this with a spring element like that. Replace this with another spring element like this. The copper with a spring element like that, and another copper element with a spring element like this. So this is my element 1. This is element 2. Here is element 3. And this is element 4. And there is my force that's being applied. So let's also put down some node numbers. Put down some node numbers. So this is node number 1. There is node number 2. There is node number 3. Node number 4. And node number 5. Okay? Each one of these spring elements have their own stiffnesses. In other words, stiffnesses. So for example, the stiffness of this, I'll call it K1, is equal to its length, whatever it happens to, its area, times its Young's modulus divided by its length. For the second spring element, K2 is going to be A2 E2 over L2. For the third one, it's A3 E3 over L3. And finally, K4 is equal to A4 E4 over L4. Notice that, for example, these two copper bars, they may have different cross section, as you can see. They may have different length, but the numbers you know. And what you need to do is to plug it in these equations, the appropriate length of the bar, the appropriate cross section of the bar, and the Young's modulus of the bar, and you effectively have uh, four springs with 5 nodes. Okay, so let's see now. Let me. So this is node. This is node 1. It has displacement in the x direction. Let's say that this is the x direction. So we're gonna have x1. Of course, x1 is 0. I know that. x2, x3, x4, x5. So that means displacement in the horizontal direction. At the x1 means displacement at the horizontal direction at the wall, which is 0, by the way. This is displacement at node 2. This is displacement at node 3 and node 4 and node 5. Right? Okay, so we loop through the elements one by one. One by one, we loop through the elements, assemble the matrices and the 2 by 2 matrices, and eventually apply the restraint and apply the loads and solve the problem. So loop through the elements. In other words, E equal to 1. Write down the equilibrium equation. I don't call it equation of motion here because we are assuming it's a static problem, and therefore there is no motion involved. There is no inertial force involved. So we're going to have K1 minus K1 minus K1 K1 times x left x right equal to FL F right. And these, remember, these are for element number 1. That's why I put the superscript 1 here. And you do this thing for every element and then assemble it. Now, I'm not going to go through the details because we have already done those details. So what we do, we have to put this thing in the mass in the global stiffness matrix. These are the element equations. Element equations. So the global, they're going to go into a 5 by 5. Let me put 5 rows and 5 columns here. Row 2, row 3, row 4, and row 5. Okay? Times the displacement x1, x2, x3, x4, and x5 equal to our load vector. All right. So this particular element number 1 is going to go K1 minus K1 minus K1 K1. And there is going to be F superscript 1 left, F superscript 1 right. We go to element 2, write the same thing and assemble it. So let me go ahead and just do the assembly. I'm not going to write down the equation. Let me move this thing out of the way. All right. So we're going to have plus K2 minus K2 minus K2 K2. It's going to be plus F2 left, F2 right. And then we go to element number 3. We change the color here and assemble it. Plus K3 minus K3 minus K3 K3 plus F3L F3R. And finally, let's go to element number 4. Okay, so it's going to be plus K4 minus K4 minus K4 K4. So that's going to be plus F left, element number 4, F right, element number 4. Okay, now these other things, of course, are all zeros. And as I promised you, stiffness matrix, mass matrix, we don't have here, are going to be sparse and symmetric. You can see this is symmetric. Now, what do we know about the restraint? We know that x1 is 0. That's pretty much all we know, which means that the corresponding thing on the right-hand side is the reaction force at the wall, R1, which is an unknown. X2, X3, X4, X5, they're all non-zero, and our job is to find them. How about this? Look at what it's saying. It's looking at the right force of element 1 and the left force of element 2. When you look at your diagram, that is referring the sum of all the forces applied at node 2, and there is no force applied at node 2, and this is 0. When you look at the second term, it's looking at the right end of element 2 and left node of element 3, which is referring to node number 3. It's referring to this particular node. And the sum of the external forces applied there is 0. And by the same token, this is 0. This last term down here in the load vector is referring to the right end of element number 4. And the right end of element number 4 is exactly where we applied that big force F. So this is F. So notice that if we ignore the first row of this equation, that means we only concentrate on this matrix times that vector equal to this right-hand side, we have a system of equation that can be solved. So let me go ahead actually write the reduced equation. So this is the reduced equation. Reduced equation. That means after you apply the loads and boundary condition, it's going to be a 4 by 4 matrix. So it's going to be K1 plus K2 minus K2. Remember, these are not squared. These are referring to AE over L of element 2. So K2 means the stiffness of element 2, for example. And a 0 and a 0 minus K2, K2 plus K3 minus K2, 0, 0 minus K2, K3 plus K4, 0, 0, 0, I'm sorry, this is minus K2, uh, minus K4, that's what I mean, minus K4 and K4 times X2, X3, X4, X5 equal to 0, 0, 0, F. All right? Let me insert a blank page here. Let me insert the blank page. It keeps inserting in the wrong spot, but that's okay. So not okay actually. Let's try one more time. All right, be patient. All right, there we are. Okay. All right, so here we can solve for x2, x3, x4, and x5. And now go to the first row that we ignored. The first row that we ignored. What do I mean by which row am I talking about? It's this row that I'm talking about, right there, right there. Okay, the first row. So what does the first row say? It says that R1, it says R1, reaction force at the wall is equal to K1 times X1, which incidentally is 0, minus K1 X2. Now, of course, as I said, X1 is 0, we know that, and X2, we have it from way up here, and that will give us the reaction force at the wall. So this is how things work. I'm going to do one example which involving numerical values, and that will be segment 8, and essentially completes these different segments that we have done. I don't know whether maybe we can do it right here. Okay, yeah. Actually, instead of creating segment 8, let me just continue and do the problem right here. All right. Okay, here's a situation. We have, this is an example involving numbers. This is what we got. We have a bar like that, and a bar like this, and a bar like this, fixed at the two ends, and we apply a force F here. Okay. Let me put some dimensions there. So this is 0.3, 0.3 meters. This is 0.4 meters. And also this is 0.3 meters. All right. It's made of steel. All of them are made of steel with Young's modulus in SI units, actually made of aluminum. This is aluminum. 100 gigapascal, which means it's aluminum. And the cross-sectional the cross-sectional area is yeah A. Cross-sectional area is, for this one, 10 to the minus 4 meter squared. For this one is 2 times 10 to the minus 4 meters squared. And for that one is also 10 to the minus 4 meters squared. 10 to the minus 4 meters squared means that it's the cross section is 10 millimeters by 10 millimeters. Think about it like that. It can be circular, but anyways. All right, so what the first thing we need to do is to break this up into elements. And the elements, we're going to do it like this is element number 1. This is element number 2. Here is element number 3. And there is element number 4. And the ends are fixed. Notice that the reason I broke this this part into 2 elements, because I'm applying a force in the middle, which means that I need to break it up into like that. Okay. What about the force, the magnitude of the force? The magnitude of the force that's being applied is 10,000 Newton. All right. Let's label these elements. So this is element 1, element 2, element 3, element 4. This is node number 1, node number 2, node number 3, number 4, and number 5. All right. These 2 elements, elements 2 and 3, have the same stiffness, and you do recall that at the beginning of the hour we said that each one of these have a stiffness A E over L, its own length, its own area, and its own Young's modulus. So in principle, I have to go and calculate all of these, and let me do that in the form of a table for you. So I'm going to make our job easier, so I'm going to make a table like that. It has 4 rows. All right. So these are elements. Element 1, element 2, element 3, and element 4. Element 1, the area of element 1, the length of element 1, and the stiffness of element 1, which is AE over L. All right. This was 10 to the minus 4. This is 2 times 10 to the minus 4. 2 times 10 to the minus 4. And 10 to the minus 4. The length, this was 0.3. This was 0.2. 0.2, half of this length, okay? And then 0.3. And the stiffness can be calculated. It's going to be 10 to the 8 over 3. This is 10 to the 8, 10 to the 8, and 10 to the 8 over 3. The unit, of course, the unit of this is Newton per meter. All right. Now we're going to go and assemble it into our 5 by 5 global matrix. And this is what we're going to get. We have a 5 by 5 matrix. This is multiplied by displacement x1, which is 0, we know that, x2, x3, x4, and x5. So let's see now. We need 5 rows, 5 columns. There it is. So we're going to have 10 to the 8 over 3 here, minus 10 to the 8 over 3, minus 10 to the 8 over 3, 10 to the 8 over 3. And then for the second element, it's going to be plus 10 to the 8, minus 10 to the 8, minus 10 to the 8, 10 to the 8. Oh, let's also put down our loads here. You know, I'm going to write this, but after a while, when you do some of these, you realize that this is really the right thing. The way I'm doing it is redundant. So this is going to be F1 left, F1 right, and even without doing the rest of them, you can fill in the rest of the blanks. It's going to be F2 left, F2 right, plus F3 left, F3 right, plus F4 left, and F4 right. Okay, now let's go and do the rest of the matrix. It's going to be plus 10 to the 8, minus 10 to the 8. This is for element 3 we're doing now. This is 10 to the 8, 10 to the 8. And for element 4, it's going to be plus 10 to the 8 over 3, minus 10 to the 8 over 3, minus 10 to the 8 over 3, and 10 to the 8 over 3. We know that this is 0. We know that this is 0. This is the reaction force at the wall, node 1. This is the reaction force at the right-hand wall, which is node 5, or 5. Now, this is sum of all the forces applied at node number 2, and that is 0. This is sum of all the forces applied at node number 3, and this is your 10,000 Newton. And finally, this is sum of all the forces applied at node number 4, and this is 0. So let us write this thing in a more efficient way. So our matrix equation is going to look like this. It's going to be 10 to the 8. We're going to take the 10 to the 8 out. And if I look at the reduced matrix means that you just look at this block, this 3 by 3 block right there. You look at this 3 by 3 block, because after all, we're trying to solve this equation. All right. So this is going to be 4/3 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 4/3 times the displacements x2, x3, and x4 equal to 0, 10,000, 10 to the 4, and 0. So now we can solve for x2, x3, and x4, and we have our displacements. Okay, so this thing is acting up. So you're going to go x2 equal to, you solve it, you get 0.15 times 10 to the minus 3, which means that this is 0.15 millimeters. And I will just write down the other ones. So it's going to be x3 equal to 0.2 millimeters, and x4 is going to be 0.15 millimeters. And if you want to find the reaction forces, you go and substitute in the first row that we ignored and the second row that we ignored, and you're going to get your forces. Needless to say that you're going to get R1 equal to minus 5,000 Newton, and R2 is also minus 5,000 Newton. So this is, although we didn't do this for a complete three-dimensional model, three-dimensional interconnection of springs and elements, we did it for a bar. So this is the idea behind finite elements. But when it's a 3D, this guy becomes very complicated. It involves integral, multiple integrals, three-dimensional integrals. You know, these have to be done, elements of the stiffness matrix, not AE anymore, AE over L anymore, but it's going to be very complicated three-dimensional multiple integrals. That concludes the segment 7, and I hope that you have a better idea of what's inside of that black box. All right, folks. Thank you for watching these video clips, and I hope you study it for the final exam too. I mean, I don't expect you to do a very complicated problem, but you are responsible for all of these things and anything that I do in class and in the lab and in the book. All right, take care.